Hello, welcome to this section on UDP and TCP. These two are the most important protocols in the L4 level. We'll cover both of them this lecture. So these are the topics which are going to be covered quickly. Now we are talking about two applications talking to each other, which are running on two different machines over the network. Now there could be something which is a web browser, which is a typical example of accessing a web page, and then that is generating some data. Either it could be a query or maybe actual exchange of information. Then the web server is going to feed a reply back with the web pages, and it is going to converse based on the action taken on the web page. Some data information is going to the web server, and web server is going to display some page on the browser. Now remember, the IP packets that we see on the network that all the routers are busy routing, they need to be generated by somebody, and that has to be some application based on some user interaction, or it could be a background process also, but some machine somewhere sitting somewhere is generating some information which either could be over TCP or UDP. Okay, the application is what is generating the data, but it may take a two different paths. Finally they are both of them land into IP, and of course based on whether you have Ethernet or a Wi-Fi, that L2 level data frame is generated, and then it goes on the network. So finally it is received by somebody, and then it will respond back with something, and it goes back. So this is how the entire process happens, and this is how you see a traffic on the network. As we all studied, the routers on the way only interested up to IP level, and then they put it back on the network they are connected to, and travel happens. Now IP packet itself is nothing but having some data coming from the L4 level, which is either maybe from TCP or UDP, right? So let us see that now which is actually making this entire thing happen on the network. It's because of we opening a browser and multiple tabs we use, and we normally browse on the net. So here suppose there are, how many tabs are there? 4 tabs are there. Then most probably there are 4 processes running on the system where this browser is running. So if you have happen to see a Chrome and open some few tabs and then go to the process information and then try to see the number of processes running, you will normally see not one single instance of a Chrome. There are multiple instances of Chrome running on your machine. That means there are, for each of the pages that you have, there are one process running on your computer. Now why do we need them? Because imagine a situation where you have YouTube you have, and then you are playing the YouTube. Now whether you are actively on that tab or not, that YouTube will be playing, and maybe you are not watching that video, but it will be progressing further. And similarly there can be multiple tabs which are interactively working with other web servers. So they are all individual independent processes. Some may be interactive web page where unless you give some input, that web page is not going to be refreshed, but places like where YouTube or you are getting into a call and some conference Google Meet or something is happening on one tab, that will be happening anyway even if you switch over to some other tab. So that's how the data is flowing, and the different processes are handling it. So here some example of Chrome, multiple processes running on the system, and each of the sub processes are meant for one particular connection you have established with the web server. Now all the TCP connections, normally the web servers are actually establishing a TCP connection, and this is how they are. You have multiple web pages open, so they all individually create multiple connections on TCP, and then it goes through maybe different medium and then gets out of the particular machine, and then it goes on the network and then comes back in some other web server where it is running on that machine, and then it traverses back in the reverse direction on the OSA layer. Now different web pages are shown here. Each of them are establishing a connection with the web server. That could be for different, it could be a Google server, or maybe a YouTube server, or it could be anything, but they may be on different machines, and they may be the web server may be providing different services to you. Now, what are the basic services that we need? Okay, what is there? Any application running on top of L4 is expecting something from the L4 layer, right, which is nothing but TCP or UDP. Now, what are those different things? There are different transport protocols employ different combinations of these algorithms. We normally call this as a services provided to the application. Always remember, services are the lower layer providing it to the upper layer. So in our case, we are calling anything above L4 as application. So applications are getting some services from the L4 layer. Now, what are those application services? Simple asynchronous demultiplexing service. That means demultiplex means multiple streams are coming, and they are, or it could be that you are multiplexing multiple streams, or demultiplexing means you are receiving some data and then distributing it to different pages. Now, in our good example is now web pages we saw, the web servers of different machines are feeding in to your machine for each of the tabs that you have opened. No, finally they need to be demultiplexed and provided to each of the pages on your browser. Now, another one is reliable byte stream service. Byte stream service is maybe you are having a email, or you are having a YouTube video which is running, and it could be that you are playing some music from somewhere, or maybe a movie. Then there is a byte stream of data which is coming to your machine. A request reply service, it could be that I will tell you for each of them on example. You send a request and you get a reply, okay. And service real-time application, it could be a real-time video call, or a music or a movie being played. Now, what are those applications? Demultiplexing services, UDP. Normally you want a simple demultiplexing service, even though TCP also does a demultiplexing service, but here we are talking about UDP, which is not a connection oriented protocol, wherein you just send some data, a packet which is independent of what you send next time, and then it goes to the server, particular UDP DNS server or something, and then that replies back and you get it back, okay. You are not expecting some a stream of information going here, whereas by TCP is for byte stream services, where you are calling it as a byte stream because it could be a video or audio, or it could be a movie which is being played, or a live telecast which is happening. Any of them fall into the byte stream service. Request reply service is DNS is a good example, where dynamic domain name service, wherein the browser initially, before it even goes to your web page what you are looking for, it is actually if it doesn't know where the web server of a particular URL that you are typed in, then it sends a request to the DNS server, which it knows. Maybe you will be configuring it as 8.8.8.8, or it could be some other DNS server which is configured in your machine. It goes to the DNS server saying that I am interested in getting to know about the IP address of the web server which is running for this particular website I am looking for. It could be a google.com, or it could be YouTube. So if you don't know the where it is hosted, the machine where it is hosted, then the IP address of that machine is required. Then only, if you are interested in feeding some getting some YouTube videos, it should go to the YouTube server, and that will be maybe running on some machine, and you need to know the IP address, so that finally your request will go there. So for that, DNS is used for getting the IP address. Then real-time applications could be any of the video applications. Now, having seen all this, now we are going to go into the details of how different processes. I told you that for every web page there is a different process running on this. How are they going to communicate? How are they sending the data is not a problem. Okay, suppose you are you are trying to watch a YouTube video, and you have sent the exact link of the YouTube, and you have sent the request. Now finally, after DNS, you found out that YouTube where it is running, and you sent the request to it. But now that web page is open, and you want the video that you are looking for should be streamed to that particular web page, right? A particular tab on your Chrome browser. Maybe you have another YouTube video which is playing on some other tab. Now they should not get mixed up. Now finally they should land into the particular the tab that you are open for. So one good example is, maybe you are listening to some music. So it goes to the YouTube server. Now apart from this, you also have ads normally associated with a particular page. Then normally what does YouTube do is they maintain some other server wherein the ads are kept. So there are multiple requests. Even though you have opened one Chrome browser, there are multiple requests going from there, and then they are all destined to different servers, and then when they come back, they should finally land into this particular web page, right? So you may be passing from video or forwarding it. All that requests should go to that particular video on the YouTube server, and then you should get back the stream specific to that particular video. So which L4 protocol do you use it? For video streaming, as I said, it is a byte streaming, so it has to be a connection oriented TCP protocol. Now how many processes are involved in this scenario right now? Actually it is a two-way communication. Okay, remember that whatever you are sending has to be received by the server, and then it should be received, sent back by the server. So there are multiple processes running. Each of the ad windows are different processes, and there could be multiple, if I have to call each process running on the server also, then there are 4 processes involved, because it's a two-way communication. And once this connection is established between maybe process 1 to process 4, process 1 should be to process, this is a YouTube video, so it should be connected to this YouTube server. So this is the connection, and then ad server is here. So these 4 are running. Okay, whenever somebody is opening some YouTube video, there is one process created here on the YouTube server, and then it is taking care of your request. So right now there will be 4 processes running on each of the machines, and 2 are running on here. I'm simplifying it, and then 1 each on these servers which are running. Now they need to be running as long as you are keeping these web pages on. Once you close this web page, what happens? These processes get killed, and then there is a connection closure happening between these 2 and this. And once the connection is terminated, these 2 processes which are running also will be closed. So till then they need to be alive, and they need to be interacting with each other. Now we are going to talk about how is this whole thing happening. Now I am going to take an example of a simple case, UDP, before I go into TCP. In UDP, what happens? I told you that when you open a browser, you don't know the URLs, which IP address where the web server is actually hosted on. So you are sending a request. Now that request is coming like this and goes to the web DNS server, right? Now that has to go through the entire OSI layer, starting from the application data. As it progresses, UDP header will be added. Then it should be IP packet has to be created. Please remember, the routers only understand IP. It doesn't understand, though it may look into the particular application for some routing purposes, but it only understands the IP. So IP packet has to be created. Then finally, to the IP packet to travel on the link, Ethernet frame has to be generated. So all these things have to happen, and then unpacking of that happens on the receiving side. This is very obvious. Now DNS request goes, and then you get a server reply coming from there. So when I say UDP is connectionless, what I mean by that is, you send the UDP request and there is no any state maintained here, though there will be information that I have sent a request, but it's not that you are establishing or making sure that this request I sent is actually received by the other side or not. Okay, there you are not expecting an acknowledgement from the other end, but though you are expecting some reply to come from. Suppose you send a UDP request, okay, and it doesn't get a response. What do? You time out on this side the application, and then it will send another UDP request. Okay, it may be trying out multiple times to get it, but there is no acknowledgement for every UDP packet delivery from this receiver side. Okay, so that is what I mean by connectionless. Now connection oriented, wherein I will come to that when we talk about TCP. Right now, let us defer it for some time. So now the question is, how do we identify? So I told you that data is coming from 2 different sources, and you may be having multiple tabs and running multiple YouTube videos. So YouTube video belonging to this particular concert should come in here. Now how does the receiving desktop knows that which data belongs to what? Because finally they are all coming in as a IP packets, right? Inside the IP packet you will see UDP or a TCP header. Now there should be something in the TCP header or the UDP header to recognize that which application I should feed into. So, or when I say which application mean which process also. Okay, it could be that different processes are running and I should identify the process. Now how do I do that? Now it should be remember that when I am sending the request, the packet goes to the other side, and then this sender, YouTube video server or somebody is going to create a packet. It is going to fill in some data on the UDP header or a TCP header and then send the packet to you. What you sent is not going to come back to you. It is what you are receiving is somebody has filled in for you, making sure that it is going to come to you. That means the sender is the sender, in my opinion, in our discussion, and then this is the receiver, and when it is reply, that becomes a sender and this is become a receiver. So they need to know whom they are talking to. It's like when you are calling someone, the other person is picking up the phone, and both of you are aware that whom you are talking to. Similarly, the processes, right now there are no human beings on both ends. There are two processes running and they need to know whom they are talking to. So there should be some information sent from here so that the receiver knows and then it will respond back properly. So what do I send it? Now one option is I have multiple processes running here. So let me decide that I will send PID of all of them, because I know that all of you are aware that PID 1, 2, 3, 4, whatever you have, they are all unique PIDs. But can I use PID as a unique identifier? The problem is I may have a Windows machine running on one machine, or there may be a Linux running on another, or maybe a Mac OS running on some other thing. Now each of them are they are having different way of representing PIDs. Okay, and if I have to bring in some uniformity in my protocol, because I am going to fill in this information in my TCP header or UDP header. I cannot keep this field that I am keeping it for this particular field open-ended. So I need to have a specific bit associated with particular thing to identify. Now I can't keep it open-ended, so process ID will not be a good option. Okay, because some may be 30-bit wide or it could be 64. We don't know. It depends on the different OSs coming, different versions of OSs coming. I cannot change the UDP protocol and the TCP protocol header based on the OS being released, right? So the process ID being used for identifying individual processes is not a solution. So that's what I am trying to say. So interaction has to happen, but PID is not a solution because we have different kinds of OSs running and their PID bits are different, and my protocol field cannot be modified or changed based on the OSs being released. Okay, it has to be fixed. So PID is not a solution. Now what is the alternative solution that they have come up with, the people who have defined this TCP protocol, TCP IP protocol? Port ID. Now what is the concept of port ID? Let me explain. Now suppose each Chrome window you are opening, okay, each window, okay, each of them are one tab on your Chrome. This is one tab 1, tab 2, tab 3. Now they are all from one common application, Chrome. I told you that each tab has a different process, no problem. Okay, I will have a PID 1, 2, 3 different processes I have. Now I need to generate a packet. Imagine that already URL is resolved and then you are maybe in all the tabs you are running a YouTube. Okay, then I am creating a TCP connection. It could be UDP, but let us take an example of TCP here. Now what do I do to fill in into some TCP header? I need to have unique identifier. So let me say that I have given a 16-bit field which is called port ID. Now what I do, there are some numbers 16,000 or maybe some number which is more than 16,000 to 65,000, okay, which is 2 power 16 minus 1. Now this is the range of port IDs which are actually given for any application to make use of. Now what do I do? Instead of PID, I am going to use different port IDs, and that is also who is doing it. Is it the process or application doing? No. The problem is it's not that only Chrome is using the TCP. It could be that I have a Gmail application or a Microsoft email I have opened. That application may be using it, or I may have a different other Skype application, or I am having a Zoom call. then Zoom is using the TCP. So TCP is not one common resource available to you for a particular process or a particular application. It may be multiple applications are using the same TCP which is being supported by the protocol stack. So I need to make sure that whatever I fill in my port ID, in my TCP header or UDP header has to be independent of the application. It should be independent of the processes. So it is port ID. That means I need to allocate different port IDs for different applications. The order in which they come to the protocol stack saying that I want a TCP connection to be established may be different, but there is one person allocating the PIDs for all of them, port IDs for all of them. That way I am making sure that every TCP connection or a UDP connection that I am request I am sending get a individual, independent, unique port IDs. So I have a very wide range of 16,000 to 65,000. So enough numbers of port IDs I have. You are not expected to run that many applications in your program, in your particular machine. So the port IDs are generated and it is used by the applications when they are establishing it. So what happens is, application is here, a process, application process, it is waiting on some port ID. Now this port ID is allocated by the L4 layer. Okay, L4 is the entry point to my protocol stack. So that protocol stack which is making sure that the port IDs are allotted and given to the application. Then the application waits on the port ID. Now port ID gets into the header and goes across there. Now apart from this, I need to have four-tuple value. Okay, what are those four-tuple? Now on the sender side, here let me say this is TX and this is RX, some web server or whatever. Well, yeah, I will have four values. One is source. Okay, let me write it as source port ID. Okay, and then let me call some destination port ID. Okay, which is actually here as far as this machine is concerned, and then I have source IP address, which is this wherever this machine is, and then this machine is somewhere else which is also having IP address, that will be destination IP address. Now imagine if I have these four as a single unit, okay, then I can uniquely identify any TCP socket. I will call it as a socket now. Okay, socket connection now established between two machines. So port IDs are allotted on this machine. Okay, source port ID is allotted on this machine. Source IP anyway is given by DHCP and then it is available on source IP is available. Okay, these two are taken care of. Now who is giving the destination port ID? And how do you know destination IP? Destination IP you know based on the DNS, because you know which web server you are looking for and its IP address you know. So destination IP is given by DNS. Okay, this is taken care of. Now the only question is how do I know the destination port ID? Okay, that has to be unique, I said. But imagine I am accessing a website. There is a web server, right? And that web server is expected to wait on some port ID 80. Okay, or email, that may be SMTP, that will be waiting on some other port ID. So this destination port ID is already given to you. Okay, it is for particular service that you are looking for. Okay, so if you are accessing a website, or maybe YouTube also finally is a website, so youtube.com, right? So 80. Now you will put a fixed value here, but that doesn't mean you will have a problem when the data arrives at your end. No, because one of these values should be unique. So imagine you are running two YouTube videos in your machine. Then your source IP will be same, because both the YouTube videos are using the same IP address on the machine. Okay, very good. Now you are accessing YouTube only, so that means the destination IP will also be same, because YouTube server is running on one machine. You will be accessing that only, so that is also same. Now destination port ID, I told you that no, YouTube itself may be a web page, and then it could be a port ID which is unique. So that specific particular port ID, that will also be same. So what is different here? Only difference will be different source port IDs will be given, because your YouTube video 1 is running on one Chrome window, and another YouTube video may be running on another Chrome window, or maybe another browser itself, maybe from some other browser, IE or something, you are accessing the YouTube. So that will have a different port IDs. Okay, so basically one of this should be unique for you to have a unique connection. Now look at from the destination machine side. It is getting the request from two YouTube video requests are coming from the same machine, but still it has all these four values that you have given is going to the packet here. So this machine also will have all these four information. So always the any connection that you establish between two machines, they are tied up based on these four values, and the same four values are visible here also, which is going, how is it visible here on the destination side? It is going as a packet, in the packet. So if you look at the TCP header or UDP header, you will see that all these four entries are there, which is delivered to the other end, and they are coming back to you also in the same way. Only thing is, when it is going, where it is occupying the places will be different. So here source IP address and destination IP address will be here, right? But when it is coming back, destination IP what you sent will be a source IP, and then source IP what you sent will be a destination IP. The location in that header will be different, but finally all the four values are coming to you. Okay, source port and destination port, from here it is a source port, destination port will be there. From there when it is coming, it is reverse and then coming back to you, but the same four set of values are going from here, and the same set of four values are coming back to you. So there is no confusion in terms of establishing who is talking to whom. Okay, so I hope this is clear to you. Once this is clear, the rest of the video will be just to summarize on whatever I told you. So this I am just running it, this header, things are unique, source of port IDs are given. That's what is done by the allocation done by the protocol stack L4 level. Different port IDs are there. Source port ID is given to every connection that you are establishing, unique, but destination port ID could be same, it doesn't matter. Okay, because one of the values should be unique out of four. So destination port ID clients, you will get the same port ID which I have explained to you, because you are talking to the same YouTube server or the same ad server, and they will all be waiting for the connections to be established on the same port ID. So destination port ID and the destination IP will be same from the sender perspective, but who is asking will be different. The source port ID will be different. Okay, so there are standard port ID. That's why I told you that each of those applications, FTP or SMTP, mail or DNS server, all of them have TCP. I told you, HTTP is 80. All of them have unique port IDs. So these port IDs are unique, but these are all normally they are all service providers, so service port. So they will all be, from the sender perspective, it will be a destination port ID, but sender is getting the unique source port IDs. So there is no problem as far as this four tuple is concerned. One value is different. Okay, so this is what about UDP. Now let me just explain quickly about port numbers. I told you that the port numbers are 16-bit wide, so they are the numbers which are mentioned here, and then length field is actually taking the data also into consideration. It will calculate the number of bytes, okay, and it is split into 16-bit. Then you know that the data portion, the entire UDP cannot be more than 2 power 16 or 64K, and then you calculate the UDP checksum, including the data which is being part of it. So I hope now you can understand and what is going into the each of those fields of UDP header. Okay, now one unique thing about the UDP is pseudo header is there. Okay, now let me talk about what is pseudo header. Apart from this, okay, protocol number, pseudo header consists of 3 fields from the IP header. Okay, if you recall the IP header, there was a protocol field in the IP header. Now you know that this UDP is going to sit on IP packet, right? So IP will be having the header and it will have its own protocol. Now whatever UDP or TCP it is initiating, that protocol number will be part of the IP headers field, which will also be considered for the pseudo header for computing the checksum. Now, what are the things taken from the IP header is the protocol number, either UDP is initiating or TCP is initiating, source IP address and destination IP address of the machine from where it is going, the packet is getting generated. So, the UDP checksum includes these fields also. Now, what is the reason? Now, let me explain that in the next field. But yes, the UDP length field is included twice in the checksum. Now, again, the UDP header is also UDP length field is also considered. Okay, it is computed twice. Now, what is the purpose of pseudo header? The motivation behind having the pseudo header is to verify that this message has been delivered between the correct two endpoints. Because I told you that source port ID and destination port IDs are there, and the unique endpoints you will consider only when you have IP header, the source IP and the destination IP also. So, if the checksum is including all four of them some way or the other, then if any of these fields are different, checksum will not clear, and the mishandling or delivering of the UDP packet on the receiving side will be ignored. Both on the receiving side, anywhere you are receiving it, if you are only considering, suppose if you want to make sure that the four tuple values are unique, you need to consider not only the port IDs of source port ID and destination port ID, you need to consider the IP addresses also. So, how will you make sure that the packet is not tampered with on the way or misdelivered? Maybe which is meant for some other machine, somebody else has created a UDP request and then it lands on your machine. Then it should not be happening, right? So, you have to make sure that UDP checksum takes care of that. So, that's why they have included the source IP address and destination IP also in the calculation of UDP checksum. Okay, so that's all I want to say. So, how it is finally coming back to you? It is each of the processes are waiting on particular ports. It could be multiple processes waiting. It is supported by the OS. The queues are, if you have come across the message queues and all that, then they are all used here. Okay, OS is coming into the play, but the protocol stops here. Later on, OS is taking care of, and then application is interacting with the protocol stack using the OS supported features. And one more thing you remember, even the protocol stack is running as a process. Okay, UDP or TCP, they are all protocol stack, they are also running as a process. So, it's an interaction between two processes happening. So, data is coming from the network, and even maybe IP and other things also will be processes, because segmentation, reassembly, all those things are happening at the different level, right? So, different processes are communicating between them. There may be a shared buffer between them to share the information. Finally, the application will be coming, and if there is a change in the mode, then the protocol stack will be on the kernel mode, and then application will be on the user mode. So, it will be buffer, packets will be, the data will be copied into the user process, or it will be shared. There may be a shared memory also. So, all the OS concept that you learn will also be used underneath when the network protocol is running in your machine. So, key features of the applications: connectionless. Now, UDP is connectionless because you don't expect a response for every packet that you deliver. There is no guarantee. Okay, unsequenced. You may whatever order you are sending, they may not be receiving in the same order. Unreliable. Some may be lost, and one advantage is low overhead. Okay, so no acknowledgement is needed. No flow control. Now, what I mean by flow control means you cannot stop generating the UDP packet, because there is no way of saying that the network is congested or the server is not able to take your request, so please slow down. That is not possible. Whereas in TCP, you can actually slow down the generation side of your data. Okay, so suppose if you are broadcasting some live music program or a lecture, then you actually, if the network is congested, you may see that the quality of the video received on the other end will be poor, because the sender is blocked from sending high definition video. So, it may slow down to maybe a low definition video on the network. So, duplication and loss, all those problems are there in UDP. These are the issues with the UDP. And voice over IP usually uses UDP, because if suppose you are sending a voice packet and it is being sent on the internet, and if it is not reaching on time, there is no point in sending that delayed packet further down. and you cannot actually establish a connection. TCP normally takes a little bit of no connection establishment and then tearing it down the connection, so that will be an issue. So UDP uses only Skype uses only UDP for communicating voice over IP, okay, application. Okay, so this comes to the end of UDP. So maybe I will talk about TCP in the next lecture. Okay, bye bye.